Good morning, everyone. Let's just wait a few moments till everybody comes in. How are we doing? I'm all right. Questions while we wait? Right? I mean, we're almost there. 2000. Today we're going to start looking at tests for convergence. Before we do that, though, we'll do a few more examples of what we were doing last time. While we wait for others to come in, why don't we do a few exercises? Related to what we were looking at. Yeah, we're still on 11.2, that's right. But we will do 11.3 as well. Yeah. All right, consider this. Question is, does the series converge or diverge? Why don't we take a moment to rewrite this in a nice closed form. If we can, I mean, it's not immediately clear that this can be done. I mean, if we forget these two things for a moment, 9 over 4, which is 3 squared over 4, and then here you've got 3 cubed over 4 squared. So that kind of gives you the flavor of what's happening, right? Maybe powers of 3 here. And on the bottom, maybe you got powers of 4. But here the power is 1 less than the top. So 4 to the n minus 1 perhaps. And where does n start? Here, this would correspond to n equals 2, n equals 3. So that should be n equals 1. And that should probably be n equals 0. Let's see if it works. No guarantees, right? If n is 0, this is 1. This is 4 to the negative 1. And because it's a negative exponent, it flips and it gives you the 4. Looking good. When n is 1, this is 4 to the 0, so that's gone, and that's 3. Exactly what we want. When n is 2, I mean, we know that that's what we get, right? 3 squared over 4. When n is 3, 3 cubed is 27, over 4 squared, which is 16, and so on. Looks pretty good. Looks pretty good. Why don't we take out a 4 to the negative 1 here? Or let's rewrite this as 4 times 3/4 to the n. Right, I've taken out the negative 1. So I have a 4 to the negative 1 in the bottom, which is really 4. So this is the same thing. And the convenience of doing that is that you now recognize this as a geometric series, a convergent geometric series, because 3/4 is less than 1. Convergent geometric series, where 3/4 in absolute value is less than 1. Not only does it converge, but we know what it converges to, and that's equally important. What does it converge to? Starting at 0, this converges to 1 over 1 minus 3/4. Or 1 over 4 minus 3 over 4, which is, as suggested by Juan, this is 16. The series converges to 16. Well, I mean, we didn't show the whole proof that it converges, right? We just used the result, right? We know that geometric series converge if the base is less than 1 in absolute value. So that's what we used. We didn't go through the whole proof of the convergence of the geometric series. There it is. Consider this. We need to show what it converges to, absolutely. If you know the series, if you know what the series converges to, you really should show it, even if they're not asking. Here again, you recognize that this is a geometric series, right? If you factor out the 5, this is really 1 over pi to the n. And again, 1 over pi, 1 over 3.14159, something like a third is less than 1 in absolute value. How do we get the 3 over 4? This is here, this is 3 to the n over 4 to the n times 4 to the negative 1. And 4 to the negative 1 here is really 1 over 4. And when you divide by a fraction, it's like multiplying by the reciprocal. So that's why it's 4 times 3 over 4 to the n. Once again, convergent geometric series. What does it converge to? Well, now it's a bit different. Here we're starting at 1, right? Our formula is valid when you're starting at 0. Here we're starting at 1. The formula is different. In fact, let's take a moment to get a general formula starting at any value k. In general, if you take a to be less than 1 and consider the series a to the n, where n starts at k, right? We have a result when k is 0. But let's get a result for any value of k. What is this? This is a to the k plus a to the k plus 1 plus a to the k plus 2, and so on. If you factor out an a to the k, this is 1 plus a squared, and so on. And now here you recognize the usual geometric series. So this is a to the k times 1 over 1 minus a, right? Because a is less than 1 in absolute value. So here we go. We have a nice general result starting at any value k. And there is the result. It's really the first term over 1 minus a. If k is 0, the first term is 1, and that gives you the original result. So it's really a generalization of what we've seen before. So let's finish that up then. This is going to converge to 5. First term, 1 over pi over 1 minus 1 over pi. I'll let you simplify that, but there it is. Louise is asking if we could just use a substitution to shift the indices. Absolutely. Very nice. You can do that as well. Alexandra is asking, why is it 1 over pi over 1 minus 1 over pi, not just 1 over 1 minus 1 over pi? Well, I mean, the answer is right here. I'm starting at n equals 1 here. The result you're stating is when n is 0. If you're starting at 0, it's 1 over 1 minus 1 over pi. Starting at 1, it's different. Nikki, it's better to simplify. The audio clips a lot. Is it for everyone? How's the audio? Is it just for a select few, or there's an issue with the audio? Audio sounds fine. Very good. Thank you. All right. And Charles gave us the answer here. Thank you. Charles gave us the answer for 38. First of all, don't let the k fool you here. It's just a dummy variable, right? Whether it's n or whether it's k, it's the same thing. And Charles suggested that if we look at the limit, this has the form infinity over infinity. So you can apply L'Hopital's rule or factor out a k squared from top and bottom. Let's do that instead. It's going to be slightly faster. If you factor out a k squared, 1 minus 2 over k plus 5 over k squared. The k squares cancel. As k goes to infinity, 2 over k goes to 0, 5 over k squared goes to 0, leaving you with a limit of 1. 1 is not 0, so diverges by the divergence test. Very nice. After Dom is suggesting after k equals 3, the denominator is smaller than the numerator, perhaps. But we cannot just state that. You have to prove it. And what you would be suggesting in that case is that the limit cannot be 0. And I think it's much easier just to apply L'Hopital's rule or work out the limit. Would you have to write infinity over infinity on an exam? You don't. You don't. I mean, it's fine if you do, but you don't have to. The important thing is to evaluate that limit. What would we do in an example like this that doesn't diverge with the divergence test? Well, then you have to do something else. The divergence test will tell you no information, and you have to do something else. Vishal is asking, isn't there the polynomial test? I don't know what that refers to. I've never heard the term polynomial test. Is it a good habit to always start with the divergence test? Well, I mean, look, if you have a lot of experience with these things, oftentimes just by looking, it's immediately clear. If the limit is 0, you know you don't have to waste any time. If the limit is not 0, then you're done. Yeah, we shall. I still don't know what that refers to. Yeah. All right. Let's move on and consider this. Charles is suggesting maybe the polynomial test was the p-series. We're actually going to see the p-series momentarily. Is there a way to find that it diverges by doing a telescoping sum in the case of number 38? Perhaps. Perhaps. I don't know. I don't know. I'm going to let you work that out. I suspect not. So, I mean, if you're referring to not just number 38, we actually did see an example of a telescoping sum which diverges last time. So you can look at the previous video. You'll see. Somebody's suggesting that we can split this series into 2, and the 2 over n diverges, so the whole series diverges. And that's actually true, but are we convinced? Right? Here's the thing, right? This part is a convergent geometric series. This part is a divergent series. So now we're asking ourselves, if you have a part of it which converges and a part which diverges, does the sum necessarily diverge? The answer is yes. And let's prove it. if the series AN converges and the series BN diverges, then the series AN plus BN diverges. And perhaps you're thinking to yourself, this is trivial because I can just split them up. This one converges, that one diverges, and consequently the whole thing diverges. But you're not allowed to do that. You're only allowed to do that if both converge to begin with. So Justin is suggesting divergent plus convergent equals divergent, and that's exactly what this claim is saying, but we really need to prove it. And let's prove it. Let's prove it. And the proof is very nice. Again, it's a proof by contradiction. Suppose not. In other words, suppose this sum converges. Right? Suppose the sum is actually convergent. Then what? Since this converges, too many thens. Then since this converges, the sum or difference is going to converge. Right? And now since both of these converge, you can combine them together and get AN plus BN minus AN, which is just BN. Right? So if this converges, since this one converges as well by assumption, then the difference is going to converge, but the difference is Bn. Contradiction, because the Bn is assumed to diverge. Well, it's a proof by contradiction, right? So if we suppose that the statement is false, then this should converge, but we quickly run into a contradiction. So Nikki is asking, can we combine in one sum only if they both converge or both diverge? You can only combine them if they both, well, I mean, it depends what you mean. Perhaps I'm reading too much into that. But to go from here to there, this can only be done if both are convergent. Let's say that. Why does the difference necessarily converge? Well, I mean, you know that result. This is a result on sequences. If you have two sequences that converge, their sum has to converge as well, or their difference in this case. Well, this means proof. I'm proving this claim, and I'm saying suppose not. It's a proof by contradiction. Suppose the result is false. In other words, suppose that the series AN plus BN actually converges. All right. So conclusion, If one series converges and the other diverges, then the sum has to diverge. And so this has to be divergent, right? This one is a convergent geometric series. This one diverges. We proved that last time. And there it is. Somebody wants me to go through the proof again. I'm saying, suppose the statement is false. Suppose that the series actually converges. You know the sum of two convergent series is convergent, and you can split them as you wish. So this one is convergent, this one is convergent, so I'm going to subtract the two. And I can rewrite them into a nice, a single sum, right? This converges, so I can split or regroup as I wish. It's a nice property of sequences. And you know a series is really just a sequence of partial sums. Somebody's asking, will proofs like this be on the exam? Who knows? We'll see. Somebody's asking, how does 2 over n diverge? We actually proved that last lecture. A few people are asking, why does 2 over n diverge? We proved it last time. So have a look at that. That's the beauty of these recorded lectures, right? I can now just refer you back to the previous lecture, and you have the added bonus of looking at me do that proof again. Let's not worry about the exam for now. People are worrying about the exam. Let's worry about learning the material. Louis Julien is asking, we don't have to prove that 1 over n diverges. We can just assume it. Everything we prove in class, you can now take as granted. So we proved it. Facts indeed. Consider number 50. One last example, then we're moving on. Well, I mean, we're maybe moving on to nice exercises, other nice exercises. Does the question, does the series converge or diverge? Diverges, why? Yes, very good, diverges, but Ariel is suggesting maybe a divergence test. And this has the form infinity over infinity. So we're going to do a L'Hopital's rule. This is e to the n over 2n, which still has the form infinity over infinity. One last L'Hopital's rule is going to give it to us. Differentiate the top, differentiate the bottom, and the limit is infinity. Infinity is not 0, so diverges by the divergence test. Very nice. Very nice. Mathieu is asking, why does the last line of the proof show that Bn converges? Here we have a convergent series. Here we have a convergent series. So the sum or difference of convergent series is convergent, and you can group them together. So this, which is equal to that, is convergent. But this is just that. let's see a nice application of these series. In high school, we were given a definition of rational functions. Perhaps you were given the same definition, but we were told that rational numbers are numbers whose decimal expansion either terminates or repeats. So that's the definition, at least I was given in high school. Amanda's asking, if we know the exponential function grows faster than the polynomial function, do we still have to prove this limit? Yes, you do. Let's wait a moment till the freeze. Is it still buffering? Let me know when you're back. What is the third word? R? It's back. Very good. Excellent. So rational numbers are numbers whose decimal expansion either terminates or repeats. That was the definition we were given in high school. Or at least I was given in high school. But then when I got to university, suddenly we're using it different. Still frozen? Jeez. Well, I mean, hopefully you'll be able to catch the video. Yeah, and then when I got to university, suddenly rational numbers are what? Are fractions. Are fractions of integers. So that's kind of weird. Two seemingly very different definitions. Are they the same? First two words, rational numbers. So two seemingly very different definitions, are they the same? Do these two different definitions correspond to the same set? That's the question. And to that end, let's take an example. Number 54 is asking us to express the number 0.464646, where the 46 repeats as a ratio of exponents, of integers rather. as a fraction of integers. And let's see how to do that. Well, exactly, right? A few people are beating us to the punch right there. But 0.46, 46, 46, this is really, this first 46 here is 46 over 100. And then this second 46, you've got 1, 2, 3, 4. 1, 2, 3, 4. So it's 46 over 10,000. And then you'll have a 46 over a million. And so on and so on. In other words, 46 over 100 plus 46 over 100 squared, 46 over 100 cubed, and so on. So if you factor out a 46, this is 1 over 100, 1 over 100 squared, 1 over 100 cubed, and you recognize a geometric series. You recognize a convergent geometric series. What does it converge to? This converges to the first term over 1 minus 1 over 100, which, as suggested earlier, is 46 over 99. And if you enter 46 over 99 on the calculator, you'll see that it gives you 0.46, 46, 46, where the 46 repeats. Let's do another one. 51, the question is asking us to repeat with the number 0.99999, where the 9 repeats here. Right, so again, 0.999 with a repeating 9, this is 9 over 10, right? That first 0.9, and then 0.09 is 9 over 100, and then 9 over 1,000, and so on, or 9 over 10, 9 over 10 squared, 9 over 10 cubed. If you factor out the 9, 1 over 10, 1 over 10 squared, 1 over 10 cubed, again, you recognize that what you have is a convergent geometric series. What does it converge to? First term over 1 minus 1 over 10, which is 1. Which is 1. The number 0.99999, where the 9 repeats, is equal to 1. How are we doing? Questions here? Kareem is asking if this is a problem that 0.99999, where the 9 repeats, is equal to 1. Not an issue for me, but I mean, it's interesting. What are the implications here? One implication is that numbers don't have a unique representation. The number 0.99999, where the 9 repeats, is equal to the number 1. And in a similar fashion, the number 1.99999, where the 9 repeats, is equal to the number 2, and so on and so on. So there's never a unique representation for two numbers. Two numbers always have at least two different representations. But we're talking, I mean, Gabriel is asking, isn't it more like 0.999 converges to 1? But if we're talking about the actual number, 0.999, where the 9 repeats forever, that is a real number. That is a real number. And what number is it? It's actually the number 1. All right. Let's move on. Let's move on to tests for convergence. You know, the series, as we've been discussing them, inherited the sigma notation from Riemann sums. And the obvious question arises, is there a relationship between a series and an integral? And the answer is yes. Via the following integral test. Let f of x be a continuous positive and decreasing function where f of n is equal to an. The series an converges if and only if the integral converges. You are allowed to attend any tutorial you want. All the tutorials are supposed to cover the tutorial questions that are posted ahead of time. So it really doesn't matter which one you attend. And the meeting details should be posted on my courses. If and only if means it goes both ways, absolutely. Absolutely. In other words, if this converges, then that one converges, and vice versa. If that one converges, then this one converges, or the converse, right? If this one diverges, then that one diverges, and vice versa. Let's prove this. We'll prove it for two reasons. Dan is asking, can n equals 0? Absolutely, right? I mean, it's going to come out of the proof that we can adjust the starting position as well. Nothing is mandatory. You know, I mean, you do whatever you want. You don't even have to attend these lectures. You know, I mean, you're only marked on assignment and the exams. So you are encouraged to attend the lectures. You are encouraged to go to the workshops and the tutorials, but everything is really up to you. Anthony is suggesting we have to prove that the function is decreasing first. Absolutely, right? You have to make sure that you're in a position to actually use the integral test. Let's prove it. Again, we're proving it for a few reasons. First of all, the proof is very easy and straightforward. Secondly, the proof actually gives us more information than the actual statement of the theorem. All right. So let's prove that. And the proof comes to us via the form of a graph. We have a function that is continuous, positive, and decreasing. So our function is going to look something like this. I should have added here on the interval 1 to infinity. Right? Because that's all we're interested in anyways. So on the interval 1 to infinity, your function is continuous, positive, and decreasing. What we're going to do is we're going to partition the interval 1 to infinity into a regular partition where each subinterval has length 1. And let's calculate using this partition, right? So that's going to be our partition P. We're going to calculate the lower sum. We're going to calculate the lower sum of the function on this partition. So on your first symbol, we're going to choose the point where the function is minimum. And of course, since your function is decreasing, the minimum occurs at the right endpoint. And we're going to draw that rectangle. And the lower sum is going to be the area of this rectangle plus the same thing for all of them. Now the width is 1. The height is whatever your function is at 2. So this is f of 2 times the width. That's the area of this first rectangle. Repeat on the next subinterval. The minimum is going to occur at 3 because your function is decreasing. So the area of this rectangle is the height, f of 3, times the width, which is again 1, and so on and so on. Now, f of 2, by assumption, is a2. So this is a2 times 1, which is just a2. And this is a3 times 1, which is just a3. And a4, and so on. I think we see what's happening. This is going to be the sum of an starting at 2. And let's repeat. Let's repeat for the upper sum. Let's work out the upper sum. Instead of taking the smallest value in the upper sum, we're going to take the largest. And your function is decreasing again, right? So the maximum is going to occur at the leftmost endpoint. And the area of that rectangle is the height, f of 1, times the width. And repeat for the next subinterval. On the interval 2 to 3, the maximum is going to occur at 2. So height f of 2, width still 1, and so on, right? On the interval 3 to 4, the maximum occurs at 3, and it is f of 3. And so on. But again, f of 1 is a1 times 1, so that's just a1. And this is a2, and that is a3. In other words, this is the sum from 1 to infinity of an. And now if we put all of this together, P for partition, it's the set of numbers 1, 2, 3, 4, 5, 6, and so on. So now let's put all of this together. You know from your work on Riemann sums that the lower sum is always less than or equal to the area under the graph, which in turn is less than or equal to the upper sum. Here, the lower sum, we just calculated to be this series. The actual area under the graph, you know to be the integral. And the upper sum is the series starting at 1. And there it is. You have this nice inequality. You have this nice inequality. Conclusion. If the series converges, meaning if the series is less than infinity, then the integral is less than infinity. Jeremy is asking, why is it 1 to infinity? Well, I mean, we have it right here. That's your upper sum. And this one is your lower sum. The function does need to be positive, absolutely. So if the series converges, then the integral is less than infinity. If the series is less than infinity, the integral is less than infinity. If the series converges, the integral converges. Conversely, If the integral is less than infinity, then this series is less than infinity. So that series is going to converge if the integral converges. Now you're thinking to yourself, well, I mean, that's cheating. This one starts at 2 when you want to conclude the series starting at 1 converges. But of course, all you're missing here is one term, the A1 term. And that is a finite term. So if you throw in a number, no matter how large it is, it's not going to have an incidence on the convergence or divergence of the series. So if your series started at 0, exactly, right? I mean, if your function started at 0 and was continuous and positive and decreasing, then you could extend this to 0 to infinity. What if there's an asymptote? Well, then that's an issue. So we want to stay away from that. It has to be continuous, absolutely. Yeah. Let me mention that without too much work here, we can extend the result, right? I mean, here we did the interval from 1 to infinity, but what if you started at some value k? Can we generalize the result? Can we generalize the result very much like we did with geometric series, right? Where we had geometric series starting at k instead. Imagine working out the lower sum on this partition. Your thoughts on what that would be, right? The minimum is going to occur at k plus 1. So you're going to have the usual, right? You're going to have the series from k plus 1 to infinity. And your upper sum is going to be from k to infinity. Right? In very much the same way that we had 1 to infinity versus 2 to infinity. If you repeat the whole argument starting at k, you're going to get this. And same thing, you're going to get the lower sum is less than or equal to the actual area, which is less than or equal to the upper sum. Namely that. Kareem was asking what about negative but increasing? And as Louise suggested, just pull out a negative, then you have a positive and decreasing function, and you're good to go. Absolutely. Well done. Right, so we can generalize to this immediately, right? A similar argument gives you that. And what? And I mean, I think it's clear. It's clear that this sum is less than that. So this is going to be less than the integral starting at k plus 1. Right? By looking at this and applying it to k plus 1 instead, you get that. And so you have this nice inequality. You have this nice inequality for the sum from k plus 1 to infinity. This sum is sandwiched between these two integrals. What's the point here? Well, the point is this. If you have a series that converges, right, you might apply the integral test and you have convergence. You can establish convergence of the series. What the integral test doesn't tell you is what the actual series converges to. So what can you do? Well, you can say, I'm going to approximate what the series converges to. I'm going to add the first few terms of the series and get an approximation. The question arises naturally, how good of an approximation is that? And somebody's asking, why did I erase the right part? Only because this is what I want to concentrate our attention to. Right? So let's say this. If you establish the convergence of a series using the integral test, that doesn't tell you what the series converges to. It only tells you that it converges. You can approximate what. Let's give it a minute. Let me know when it's back. Is it back now? It's back? Very good. So you have this convergent series. You're going to add the first n terms, right? So this is the sum, a1 plus a2 plus a3 forever. If you remove the first n terms, a1 plus a2 all the way to an, what are you left with? You're left with an plus 1, an plus 2, and so on, right? So you really have the series from n plus 1 to infinity. This is the error. It's the error, it's the difference between what the series converges to and your approximation. So this is your error term. How far away you are from the real thing. And wouldn't you know it, there it is. Here your error is sandwiched between two integrals. y is the sequence where n equals k plus 1. You say sequence, but I assume you mean series. Bigger than the integral where k from k plus 1 to infinity. Well, this is due to what I had actually erased. We had actually proven this. This is what we have proven. So now if you just look at this and you replace k with k plus 1, you get the integral from k plus 1 to infinity is less than or equal to the sum from k plus 1 to infinity. But the sum from k plus 1 to infinity is what you have here. So the sum from k plus 1 to infinity is bigger than or equal to the integral from k plus 1 to infinity. Let's take an example of this. Let's take an example. Before we take an example, well, what do we want to do? Jeez. We are running out of time. Look, let's postpone this discussion of approximation till next time, till Tuesday. What we're going to do in the meantime is do some examples of the integral test, and we'll come back to that. And before we move on, consider this. Consider series of this type known as p-series. And let's take an example. 1 over n squared. Let's establish the convergence or divergence of the series using the integral test. Consider the function which gives rise to this, the function 1 over x squared. This function is positive on the interval 1 to infinity, right? I mean, the denominator is something squared, so it's always positive. Continuous. Right? Because you know the graph of this. I mean, it's very well behaved. In fact, it's differentiable. We also want to prove that it's decreasing. How are we going to prove that? If you take the derivative, which is negative 2x to the negative 3, on the interval 1 to infinity, the denominator is positive, the numerator is negative, so the whole thing is negative. The derivative is negative, so f is decreasing. So we can apply the integral test. Let's apply the integral test. And this being an improper integral, This function is an improper integral, and you know exactly how to deal with that, right? This is really the limit as n goes to infinity of the integral from 1 to n. And antiderivative, you know what that is. Minus 1 over x from 1 to n. And this is really 1 minus 1 over n, whose limit as n goes to infinity is 1. The integral converges, so the series converges. There it is. Again, they don't converge to the same thing, right? This don't read too much into that. This does not tell you that the series converges to 1. The integral converges to 1. All it establishes is convergence of the series. Let's try another example. The series 1 over n cubed. Right? Another example of a p series. This is a p series where p is 3. The function that gave rise to this is 1 over x cubed. Again, positive on the interval 1 to infinity. Differentiable, so you know it's continuous. And what is the derivative? The derivative is negative 3x to the negative 4, which is negative. So it's differentiable, so it's continuous. And decreasing since the derivative is less than 0. So we can apply the integral test. And of course, the integral which is really the limit as n goes to infinity of 1 to n. Which is minus 1 over 2 x squared from 1 to n. Which is 1 over 2n squared minus 1 over 2, whose, no, it's the opposite, sorry, minus plus, whose limit is easily seen to be 1/2. Series convert, the integral converges, so the series converges. My question to you is, can we come up with a nice general result? For what values of p do p series converge? Can we come up with a general result for p series? Let's do it. Let's do it. Observe that. What are we going to observe? Let's look at p equal to 0. If p is 0, 1 over n to the p is just 1 over 1, which is 1. So you lose that n business, and by the divergence test, the series diverges, right? Because as n goes to infinity, it's just 1. For p bigger than 0, consider the function 1 over x to the p. This is a positive function. On the interval 1 to infinity. The derivative is negative p x to the negative p minus 1, or negative p over x to the p plus 1, which is less than or equal to 0. So the function is positive, continuous because it's differentiable, and decreasing. Of course, on the interval 1 to infinity. So we can apply the integral test, and the integral of 1 over x to the p, which is the limit as n goes to infinity. Let's call it x to the minus p. And so that is 1 over minus p plus 1, x to the minus p plus 1. Which is 1 over minus p plus 1, n to the minus p plus 1, minus 1. And we're looking for the limit as n goes to infinity. What is the limit as n goes to infinity? Well, that's going to depend on what this power is. If that power is negative, meaning if you are in a situation where the n is in the denominator, then that limit is going to be 0. If the numerator is of positive degree, if the power is positive, then this is going to be n to a positive number that's going to diverge. So for convergence, we need a negative exponent for the n. So we need minus p plus 1 to be negative, or p to be bigger than 1. If it's the opposite, then, right, I mean, if minus p plus 1 is bigger than 0, in other words, if p is less than 1, then this is going to diverge. And if p is equal to 1, this does not work, because if p is equal to 1, this is not the actual integral here, right? So converges if this, and diverges if P is less than 1, but bigger than 0, right? Because that was our assumption here. And if P is equal to 1, then we are looking at the integral of 1 over x, which is the limit as n goes to infinity of ln x from 1 to n, which is ln n, which is equal to infinity. So it's going to diverge if P is 1, converges if P is bigger than 1, diverges if P is between these two values, diverges if P is 0, and if P is negative, what happens then? Right, we're looking at this. If P is negative, if you have a negative power here, this is really the same as 1 over n to the negative P, where this is positive. And this, since you have n to a positive power, this is going to diverge by the divergence test. The limit is going to be infinity. Somebody's asking if P can be a fraction. Absolutely. So let's put everything together. Was a bit of a long-winded exercise here. Perhaps we've lost track of the result. Let's rewrite it here as the P-series test. Series of the form one over n to the P are known as P-series. P-series converge if P is bigger than 1 and diverge otherwise. Well, I mean, I'm starting with 1 over n to the P, which is really the same thing as n to the negative P. And if P is negative, then this exponent is positive. Do we have time for one example? 1 or 2 examples? Let's do that quickly. And then we'll call it a day. Taken from page 758. Question is asking whether it converges or diverges. Converges or diverges. Right, let's rewrite this as 1 over n to the 0.3. And now you recognize that this is a P-series. This is a P-series where P is 0.3, which is less than or equal to 1. So diverges. That's it. What if n isn't equal to 1? It doesn't matter. it doesn't matter, right? I mean, we're dealing with infinite series here. So it doesn't matter what the starting point is. What matters is that you're adding infinitely many positive numbers together. So the first million terms don't matter, no matter how large that number is. If you add a million large numbers, maybe you get something very, very big, but it's going to be finite. So that's why, when dealing with series, really the only thing that's important is the tail end of the series. Those last infinitely many numbers. So it doesn't matter where you start, it's the fact that you're adding infinitely many numbers together that's important. If p is equal to 1, we get infinity to the 0. I don't know what you're talking about, Matthew. As somebody suggested, if p is 1, it diverges by the divergence test. No, not by the divergence test, by the integral test. Right? I mean, it's if p is bigger than 1, it converges, and it diverges otherwise. In other words, if p is less than or equal to 1. We proved the case p equals 1, that's where the ln came in. Let's do one more. Let's do one more. 1 over n squared plus 2n plus 2. And, I haven't even written down points here, and it doesn't matter, right? I mean, start them wherever you want. Usually start it at the smallest value, which makes sense. So let's discuss convergence or divergence of this series, and then we'll end it there for the day. What are we looking at here? Consider the function which gave rise to this, 1 over x squared plus 2x plus 2. This is, of course, positive on the interval 1 to infinity, right? I mean, if you're plugging in positive values of x, everything is positive here. No issue there. Continuous on its domain. And if you take the derivative, this is easily seen to be minus 2x plus 2 over x squared plus 2x plus 2 squared. Denominator is positive, numerator is negative. So this is less than or equal to 0 on the interval 1 to infinity. So continuous, positive, decreasing, we're good to go. People are suggesting comparison test, limit comparison test. The problem is we haven't discussed those yet, right? They're coming up. And I mean, it's fine if you are familiar with them, but for those of you seeing this for the first time, this is it. Very well. So all I'm saying is we're allowed to apply the integral test. And it's very important that we check that we're allowed to. Could we factor the bottom and decompose? Sure. I mean, whatever works for you. The obvious question is, how do we integrate? Turns out, I think, that the denominator is an irreducible polynomial. So factoring is not going to be a real issue here, I mean a possibility. Instead, what are you going to do? How do we integrate? You know how to integrate. Partial fraction, I'm going to say the E stands for expansion or partial fraction decomposition. I'm suggesting that it already is in partial fraction form. The denominator is an irreducible polynomial of degree 2. There's nothing else you can do here. Complete the square, thank you. Complete the square, and I think we can do that in our heads. And then, you know, since you are all experts at integration, you can integrate this in your head. Maybe you want to make a simple U substitution if you must. Nothing wrong with that. But in the interest of time, since we've already overextended our welcome, let's finish that up by saying arctan of x plus 1. Everybody with us? And as n goes to infinity, arctan of n plus 1. You know the deal. Pi over 2, thank you, Dan. There it is. The integral converges, so the series converges. There it is. So practice this tonight, tomorrow, over the weekend. We'll pick this up again on Tuesday. How are we doing here? Questions? Perhaps we're going too slowly. Maybe we'll try to speed this up next week. So 11.2, 11.3, absolutely. Yeah. Very good. You guys have a good weekend. I'll see you next time. Yeah. Well, I mean, you should, right? I mean, it converges by the integral test. We are on 11.3. People using a different book, right? I mean, we're doing integral test. So pick up any book and look for the integral test. Very good. You guys have a good one. I'll see you next week.